Okay, next we have an invited talk from Zhenyu Tian, who's our final invited speaker. Zhenyu is an assistant professor at Northeastern University and is an environmental chemist that's interested in the fate, transport, and remediation of organic contaminants. He's curious about the contaminants that are truly relevant to public health and the ecosystem. Dr. Tian received his PhD from UNC Chapel Hill, where he studied the transformation products and co-occurring pollutants of polycyclic aromatic hydrocarbons, or PAHs, in contaminated soil. During his postdoc research at the University of Washington, Tacoma, he applied non-target screening to identify emerging contaminants in water and biota. And with the research group at UWT, he identified 6-PPD-Quinone, a ubiquitous tire rubber chemical that kills Coho salmon via urban stormwater. And today he's here to tell us more about that.
Thank you. Thanks everyone, and thanks for inviting me here to introduce a little bit more about the 6-PPD-Quinone. I slightly changed the title since it's probably more suitable for the audience here. It's because this is now like ACS meeting or like non-target meeting. So we'll focus more on the 6-PPD-Quinone here. And this is really like a teamwork. As you can see, the major authors from UW Center for Urban Waters here. And this building over here, you can see the Mount Rainier, and that red building is Center for Urban Waters. So just outside, you have access to marine water. So that's convenient and also like a beautiful place to work. Except for that's like teamwork, this is also highly multidisciplinary. So we cannot have this work done without the collaborators, especially the Jim McIntyre's group at Washington State University. They are the biologists, toxicologists, and we are the chemists. We work together so that we can find what's the really important things. And of course, other groups and collaborators here at the founding source. So I put the acknowledgement twice, okay. So the story begins with a phenomenon called urban runoff mortality syndrome. It's something about salmon, as you probably know, for the West Coast and especially Pacific Northwest. Salmons are pretty important because they have fishery value and some recreational value. They are an important part of the food chain. They move the nutrients from the sea to the land, right? And also, yeah, that's part of the nutrient cycle. However, in Pacific Northwest, people observe something abnormal usually it's October to November when salmons are swimming up the creeks, especially one species, Coho salmon. They die before they can reach their habitat upper stream. Right, like normally you will see a Coho or any other salmon die after they lay their eggs, but they die before that. So that's kind of like troubling because that's threatening their population. And the symptoms are usually very, so generally you will see, I have some description. So you can see the symptom is very like signature. The salmon will be kind of like almost like lethargic or it's drunk. So it will just gaping for air, but fish don't need air from, air, right? And as well, if it can still swim, it will be swimming like in circles. So that's very weird. And usually when they show the symptom, they will be killed in several hours. So that's kind of like a mystery. And also more like abnormal is this isn't only happen with certain species. So in that time, right, Coho salmon and chum salmon, they're usually swimming up the same creeks, but you will see Coho die from that, but chum salmon is totally fine. So like why, right? And as we said, like this is a trouble because if we keep this like ratio of mortality, like 40 to 90%, then we see the curve of prediction, the Coho salmon in Pacific Northwest will die out in just a few decades, right? 30-ish. So that's pretty big issue. And sometimes, after an extensive like dry period and there's a big rain, then you will see a lot of salmon die. And for example, that week we have 5 mortality cases reported in 3 days. I'm pretty sure there are more, but just like, volunteers see those, they report to us. We go to the site and we collect water, collect the fish. And when you cut the fish open, you see all the eggs. So that's the next generation of salmon and they just don't have a chance. So for us, we need to figure out why is this happening. And before our group, as environmental chemists, work on this, our collaborators in NOAA and Washington State University, they have been working on this for a while. And what they found is you can predict the mortality risk with urbanization gradient, which is a integrated like indicator with population, especially traffic intensity. So basically, where the most like heavily trafficked area, you'll have a very high risk of mortality. And because of that, they assume this is something about the road or like road runoff, right? With that, they collected road runoff from some of the busy highways, like this one. You collect the runoff from the downspout. You dilute that because it's just like very dark and dirty. You dilute it at a few times and then you expose the fish, the coho salmon, and you found the fish were killed and they show the same swirling symptom. So from there, they know, okay, this is probably something about road and cars, but the exact chemical at that moment is unknown. So what they tried is, like in probably since like, early 2000s and 2010s, they've been working on this and people will always ask, is that metal? Is that pesticides? Is that PAH, right? So they have tried all this like potential toxicants. So they made like mixtures of all this like pesticides, made a heavy metal mixture, and nothing actually induced that phenomenon. So that's something very mysterious. And that is why we need a different method. Probably some of you already know or familiar with this. This is called non-target analysis, also known as non-target screening based on you're from United States or Europe. So the concept is even without the identities or you don't have a method for this thing, you can still detect numerous contaminants. And this is like, comparing to the conventional targeted method, this is like casting a giant net into water, grabbing as many things as possible versus fishing chemicals one by one. Has its pros and cons, but at least you can get some of these like unknown or unexpected stuff. And for this, you need high resolution mass spectrometry, as we have heard from Jonathan. You need like a high resolution instrument, like 500,000 instruments. So that is that thing. So it will tell you the accurate mass of your analyte so that you can know the composition or even the structure of these unknowns. So that's what we do. And the first thing we use the non-target method, high resolution mass spectrometry, is to figure out a set of chemical signature whenever the fish got killed, right? So we call this like Coho mortality signature. So we have this awesome citizen scientists and volunteers from different like watersheds. So what they do is normally they will just count the number of fish going up the creeks and have records. But when they see this urban runoff mortality syndrome, they will just call us and we will go there on site, collect the water, collect the fish. So since 2017, 2016, we have started this effort. So these are the two mortality events. And also we know the runoff kills salmon, right? So basically we have these multiple samples and we analyze them with high resolution mass spectrometry, and we can overlap the detected chemical features of all these samples, and we get a small subset from this Venn diagram. So this 57 features, we call it the mortality signature, and you can see some of these things are we're already familiar with from yesterday's talk, right? Like the spider chemicals, HMMM, and also the bicyclic amines. This is definite guanidine. So these are pretty common things related to road runoff. And also on the left, we can see the surfactants, right? So these are common not only to road runoff, but also wastewater kind of effluent. So polypropylene glycol or the ethylene glycol. So these are the things we detect. And with this signature, we can actually see how good are the treatment system, right? Like if we see all these things are removed after, for example, like a rain garden or bioswale, then we know it's doing good. And also more important for us is we can use this signature to track the source of the contamination, right? We want to see where the toxicant killed salmon coming from. So this is the source tracking, because we know it's something about the road, about the cars. So we just like made different sources about the cars, and you can see all this like fluids, antifreeze, motor oil, all these things, and tire wear particles. We make like solution and leachate depending on how soluble they are. And this figure is like a HCA hierarchical cluster analysis, and it's like super unsupervised. So we didn't make this order. It's just like generated by the similarity of chemicals detected here. So we can see that all these like red highlighted samples are the field sample or the runoff that kills salmon. And only one thing that's like very similar or clustered together with this is tire wear particle. So from there, we know tire wear particle is associated or like very similar with this like lethal waters. That's kind of like our starting point for next step, right? Because it's the suspect. But here is like association, not causation, right? And then our collaborator, Jim McIntyre's team, also confirmed this from the biological side. So basically, they make tire leachate and dose those to chum and salmon, and they basically see the same phenomenon, the same symptom, and chum survived the tire leachate while the salmon not, right? So from there, we can confidently say that tire leachate is lethal to coho salmon. So what are the toxicants, right? That's the real core question here. And it's natural that we're starting from the mortality signature. And because there are chemical features that we actually don't know exactly what they are, but something we can identify, but only a small part of those, right? Like we have 20 out of the 57 that we can get a standard. And then we make mixture, right? So we're just thinking if it's any of these like 20 compound that we can get standard, and we make like the same similar concentration or even like 10 times higher concentration in the road runoff, then this mixture should kind of like kill or at least do something to the fish. But the result is not. So the fish are happily swimming even when we dope this like very foamy solution in there. So from there we know it's not in this 20 compounds, or it's probably not even in the signature, right? It's something else. So we have to look for the smoking gun in a harder way, right? Like not from something you can buy a standard, but kind of like do this like de novo. So that we need to use a different method. So that's something I am specialized in. That's called effect direct analysis. So for this kind of like, you know, chemistry and toxicity associated together, usually what we do is, well, no offense, something like point at where you shoot instead of like shoot at where you point, right? You have some target compound, and then you say, oh, how bad it is. So just like that. But EDA is a different framework. Say, okay, I have a toxicity I observe, but I don't know what causing this. So starting from there, we figure out the causal chemicals. Starting from a mixture, usually these are pretty complex, like a wastewater effluent or soil that's like containing thousands, if not hundreds of things. We do bioassay or any type of like toxicity endpoint test. And we found, oh, there's some toxicity in there. And then we do fractionation or separation. So generally making your samples less complex. And then with the fractions, you do the toxicity test again, see which fractions still hold that toxicity. Then goes to chemical analysis for your toxic fraction. Usually this is non-target analysis because you don't know what's in there. And if it's still kind of like giving you a lot of chemicals, then you come back, right, to fractionation and then toxicity test. So this can go in cycles to finally reduce the complexity of your sample to a few chemicals. Then that you can have the cause of the toxicity. And this is what we do with our tire leachate, right? Like we know the toxicity is in there, and as expected, is pretty complex. Usually we see more than 2,000 features in our tire leachate. By saying tire leachate, we make this by grinding some tire particles from like 9 different used tire. We put them in a stainless steel column and we leach them by a pump for a whole day so that we can get buckets of, like tens of liters of tire leachate. And then if we put the tire leachate into a like fish tank, usually diluted like 4 or 5 times, we can see the fish die in just like 2 or 3 hours. And we fractionate the tire leachate to see what chemicals, which fraction is still toxic. Then we can get that fraction to non-target analysis. So before we go into the very detailed like column fractionation, we did some like, initial tests for basic properties. So the first thing is we want to know this is like dissolved or particle bound. Then we just use like simple sand filtration. So you can see a lot of sand in this like big column. After sand filtration, it's still toxic. So we know this thing is probably very soluble. And also we tried to add EDTA, almost like overdose the tank with like EDTA to see if this is a metal, because metal will be deactivated with that, right? But it's still toxic, so we know the toxicant is organic, not like a metal. And we also tried the cation exchange because we know in the organics there are a lot of things that's like positively charged. We want to make sure if it's a neutral one or like cation. And after the cation exchange resin, the solution is still toxic, so we know it's not a cation. So this is something organic, dissolved, and neutral. So starting from there, we can just go for the column fractionation, which will separate our tire leachate into smaller and smaller pieces. So we do this by, like starting with some of the, silica gel fractionation, and what's really giving us the resolution is HPLC column. That's like a reverse phase separation. So basically you can see it's just like cutting a loaf of bread, right? You are cutting the tire leachate composite into different fraction of polarities. And we managed to do this in like 10 fractions, and only 1 out of the 10 fraction is toxic. So that kills fish. And in that lethal fraction, we only have about 200 features. So this is a great kind of improvement because you are just reducing from 2,200. So starting from there, we wonder if we can have something over there that we can get a standard and we dose the fish, right? If that works, that will save effort. But unfortunately, even we have all these things in that toxic fraction, we can buy the standard. But again, the mixture standard did not kill. So it means we have to go even harder. 200 is still a big pool. Need to go down the scope, and this is what we do. And we first try, these 3 columns in parallel to see, okay, for each of them, we can get a toxic fraction. Can we use the Venn diagram overlapping them to see if something is conservative in all those toxic fractions? And we do have a few. So based on that, we have the confidence of doing this more like in sequence, like a sequential kind of like separation, starting from tire leachate, going through some of the silica gel column, going through 3 HPLC column, and finally starting from more than 2,000 down to like 4 compounds there. And in this like 4 compound fraction, you can see there's like a pink magenta type of color solid. And if you analyze that with high resolution mass spectrometry, you will see this formula coming out. That's C18H22N2O2. It's always in there, but unfortunately, we don't have any information about this thing. So it's like a true unknown. And it's troubling us for a few weeks, if not months. And we are trying to figure out what it is. Because for any literature or database, you don't see this thing related to tire or rubber. But then there's one day I figure out this potential correlation, right? This is probably not a chemical people like intentionally added in the tire, but it's a transformation product. And for transformation product, one of the rule of thumb is you probably have the same carbon and nitrogen number, but you will have different number of hydrogen and oxygen. So based on that, I'm searching for compounds with 18 carbon and 2 nitrogen, and I found this thing called 6PPD. So that's actually a tire antioxidant that takes about 1 to 2% of all the tire outside just running around the world. And you can buy this thing pretty easily on the industrial provider website, and you can buy like tons, if not like kilos of this at a pretty cheap price. And yeah, this is just like industrial chemical. And we just bought something like this from, you know, industrial provider, and we do like oxidation, actually also ozonation, because what we found is, you know, in the literature from the 80s, there's a chemical called 6PPD-Quinone having the same formula as our unknown, right? So that's from ozonation. So once we got this, we just kind of like do the ozonation to see if we can get the same product. So that's what we have, right? So this like lighter color, well, not very obvious on there, lighter color thing, the whole thing is 6PPD, but when ozone coming off from the top, you can see this top layer get like darker. So that's what's kind of like oxidated, transformed. And if we get this like darker part out, use the same separation scheme to get it out, we can get like purified unknown of this chemical. Right, like I thought it was 6PPD-Quinone for a while because that's the 80s paper tell us. So our collaborator asked me, "Are you sure that's dinitron?" I was like, "Why not?" And they tell us they are the you know, University of Toronto NMR group. So they tell us it's no way the dinitron has to be a quinone because the structure of this like NH, like amine group, is pretty obvious, and also the carbonyl, no, the quinone group is very clear in the H and the C NMR analysis. So that's telling me the story, right? Like this high resolution mass spec can tell us the accurate mass and maybe some functional group information, but it's not the gold standard. So for the unknown unknowns, you still need to go to NMR to get the structure elucidation. So that's what we got, and we have our thing 6PPD-Quinone from here. And we further confirm this with you know, LCMS analysis. So basically you can see the retention time matched. This is one thing is from, you know, the red line is from tire leachate, the black line is from ozonation, so they match. And also the spectrum matched pretty well, so that's the same thing. And we also figure out this is like proposed, you know, transformation pathway. So if we dose 6PPD, the parent compound to fish, it doesn't kill, so it's not very toxic. But if you dose the transformation product, it's much more toxic. So you can see again, I cannot give you the video, but we can give a shot. So this one is cool. If we just say, right. Oh, yeah. Yeah, so you can see this one on the top is field sample, and then we have another that's like a, oh, how did you do that? Sorry. So the top is in the field from 2014, and the bottom is dosing this pure chemical in the lab. So you can see how similar they are if we got a video play.
That one's not playing.
Okay, I can tell you, basically they are doing the same thing. So the head is, the head is up and it's like swirling. So that's kind of like, well, symptomatically the same. Okay, sorry about that. I should have tested. So from there, we know it's the same thing because it's causing the same symptom and everything matched. Well, this one is like update after the paper because well, that's the part I messed up. It's like a necessary mess up because our isolated 6PPD-Quinone was not very pure. So when we have a pure commercial standard, we realize our environmental estimation as well as our LC50 are overestimated. So instead of like several hundred of nanogram per liter LC50. The real LC50 is below 100 nanogram per liter. And of course, the environmental concentrations are lower. And based on this is like very toxic compound, because if you think about the concentration you just heard about other chemicals, this is extremely low. And also there are studies following our study on, the toxicity of this compound as well as road runoff. And the scientists from other countries, this one is from Canada, and let me see this one. So this one is from Canada, and the right one is from Japan. So they also tested toxicity of the 6PPD-Quinone on other fish. So this one, 2 out of the 4 fish are actually sensitive to quinone, and especially rainbow trout is actually, one of the more widely distributed fish. It's the LC50 is 1 microgram per liter, so that's still low. And brook trout is 590 nanogram per liter. And one of the Japanese fish is also sensitive, and the LC50 is 510 nanogram per liter. So the species-specific toxicity is there, and we don't understand why. But it's not toxic to all fish, but just several species. So that's it. And because we have the standard, right, like we also, not only the native standard, we also have a labeled version. So based on that, we can use isotope dilution to accurately monitor this compound in the environment. So you can see this is the spectrum of internal standard versus the native 6PPD-Q. So their fragmentation pattern is the same. The only difference is the absolute accurate mass of 5, because we are adding, mass over here. So that's labeled by Dalton, right? So that's internal standard, and we developed the method based on triple quad. So this is more like, widely used instrument. You don't need that high resolution mass spec to measure that. And based on this method, we can actually get pretty good recovery of road runoff and surface water samples. The method performance is pretty good, and the sensitivity is very good. We can measure down to, several tens of nanogram per liter. And for the sample, method LOD, we can go down to nanogram per liter level. So that's what we got from the method. And with the method, we keep our monitoring in some of the creeks, right? This is the occurrence part of this chemical. We monitor the rains, like the stormwater in Miller Creek. This one of the creek in Seattle. It's actually close to the highway as well as the airport over here. So we are doing like long-term monitoring, because this creek is known for its Coho mortality. And you can see this is not all the 17 storm, but you can see this is 10 of them. And the blue line is the hydrograph, and the red line is the plutograph of 6PPD-Quinone. So they kind of agree pretty well. And well, the numbers are too small, but you can see a lot of times the maximum concentration is above that LC50. So here you can see it more clearly. It's kind of interesting because the early times, like, from 2010 or early 2021, 2020, 2021, the concentrations are relatively low. That is because we are still in lockdown, or the pandemic disturbing. And after that, everything pick up, and you will see a lot of this events concentration get up because more people are out and driving. So you got more 6PPD-Quinone in there. So that's the local monitoring, the local occurrence of 6PPD-Quinone. And following this study, we are seeing more worldwide Canadian snow melt runoff that has that, and pretty high. In Australia, they also see that, although not as abundant. And Germany and Japan, they see this in the runoff and road dust. So it's anywhere you have affinity to road or just like traffic, you will have that. And more interesting or troubling is it's also in people's urine. And for some, well, the concentrations are low, but for some reason, pregnant women has like a significantly higher concentration of 6PPD-Quinone than other population. We still don't know why, and we don't exactly know where the source is. So that's something needs to be address in the future. Okay, so that's a occurrence, and since we know about that, we are having some, because it's an emerging contaminant, right? We want to know more about that and its properties such as solubility and the hydrophobicity. We have the investigation on that. So there's a very new article on ESPI about these properties. So generally for solubility, we just put 6PPD. Oh, so I'm. Okay, so we have the solubility tested on this chemical, generally put it in a more concentrated solution and have centrifuge for some time. And then you can measure the theoretical concentration and the actual dissolved concentration. So if it's totally dissolved, you will have this concentration along this line, but if it's not dissolved, then you will see deviation over there. So the solubility we have is about 38 microgram per liter. That's not very high, but if you consider the LC50, that's in nanogram per liter, so that's still way above the LC50 and also way above the environmental occurrence. So it's not limited by solubility in the environment. And for hydrophobicity, we are just using a very standard method to see the log KOW. And we found that log KOW is about 4.3. So that is actually related to the bioavailability. We have a question yesterday about why it's always PFAS, why PFAS is so bioavailable. I believe this part of the answer is related to this, because if you have log KOW around like 3 to 6, that's very bioavailable. So 6PPD-Quinone, that's 4.3. I think PFAS is about like 5. So that's in that area. So it's moderately hydrophobic, it's available to fish, and it's potentially partitioned to materials and source and sediment. So because of that, we also did like sorption test, and we put different like materials in there, and then we have like container, just see how sorpable this to containers with different materials like plastic, glass, and rubber. And what we found is like, for glass, this one is very good, not sortable. But for rubber and, silicone or like just like PE plastic, it will sorb to the surface. And well, let's not look at the specific. So this is more like averaged data. So you can see glass totally good, rubber and silicone, no, and plastic maybe a little bit. So that's related to your sampling. If you're sampling stormwater, you want to test about 6PPD-Quinone, please use a glass container. So leaching dynamics, we also did this. This is more about the mobility, and we found the leaching is pretty fast. Usually in 6 hours, we can see 5 microgram per gram of 6PPD-Quinone coming out. And if we do this like solvent extraction, which is pretty extractive, that give us to 15. So it means in about 6 hours, we can get like about 30% out. So that's already like rapid, but you still have maybe like 10 micrograms in there. So that's telling us rapid leaching, and also there's residual 6PPD-Quinone in there. And also because 6PPD, the parent compound, is in there. So the transformation can further goes on, and you will have new quinone leaching out. So that probably have a long-term effect. And finally, stability, we have done this just see, okay, how stable we can get with, different pH. And we can see that within like maybe 3 to 5 days, it's pretty stable, not going anywhere. After like 47 days, a pretty long time, it reduced like 26%. So I would say this chemical is stable, maybe not persistent, but it's a stable one that could linger around in the environment. And yeah, that's transformation of 6PPD beyond 6PPD-Quinone. Like we already seen some other chemicals, one compound can lead to a dozen of transformation products. Some of these have actually biological activities, and some of them are actually very prevalent in the stormwater samples, even more prevalent than 6PPD-Q. So if you're interested, read this paper, also recent, from Nina Zhao. And so that's one of the things. And remember the human urine study, right? So we actually have the same group of compound that's in, not only the tire, but also anything related to rubber. So for example, the artificial turf field, we've already seen that. And also this is my own sneaker. If you run with like Adidas shoes, the Continental in there. Continental also produce rubber, tire rubber. So that's how we detect 6PPD-Quinone in our sneakers. Generally you can see these all different things like doormat, the sneaker sole, chrome rubber in the field, and even laboratory stoppers, some of the black rubber, you all have this. So that's another paper already came out like a few months ago. So that's kind of like potential sources. We still need a lot of study along that way. So take home message, sorry, I'm a little bit long, but I think I also started a little bit later, but that's it. So this meeting is about emerging contaminants, right? Like I would suggest that really there are a lot of more emerging contaminants. I know PFAS is important, plastics are important, but for toxicity effect, you probably need something else to discover more. So non-targeted analysis, EDA, effect-derived analysis are necessary tools. And 6PPD-Quinone is prevalent anywhere close to traffic, to rubber, you will have that, and is acutely toxic to fish, not only one, but several. And then the properties I've shown over there. So that's mostly it. And maybe no time for questions, but I would like to take questions afterwards or on the HUA platform. So thanks again.